Um, I'm Ju-Whan Kim from Industrial Design Department at KAIST. The co-authors are Han-Jong Kim and Professor Tek-Jin. Growing number of people are using more than 2 mobile devices, such as smartphone and activity trackers or smartwatches. With the popularization of wearable devices, many motion sensors are now tracking your body movements in everyday life. So there's no reason we don't use these sensors for full body gesture interactions. Despite of the potential of full body gesture, it's very difficult to define a unified gesture for all users. Body language is highly dependent to culture, context, and individual preference. Different configurations of motion sensors also make it hard to define one universal gesture. One way to overcome the limitations is to make users to customize their own gestures. Customization is free from contextual dependency as well as individual preference. Custom gesture is also known to be more memorable than a gesture defined by other person. Our research goal is to propose and test a gesture authoring system that end users can easily customize accelerometer-based gestures using diverse combinations of mobile devices. We chose to focus on an accelerometer as the main gesture sensor because it's embedded in many mobile devices. It's very inexpensive and power efficient while sensing rich gesture information. However, an accelerometer is not accurate. It's very hard to reconstruct the original motions from only accelerometer values. Furthermore, the concept of acceleration is very unfamiliar to general users. If a user cannot understand the behavior of an accelerometer, then it's very difficult to define and perform accelerometer-based gestures. Existing gesture authoring systems can be categorized by 2 approaches. Programming by demonstration defines a gesture from users' performed motions. It doesn't require any pre-knowledge to define a gesture. But when an error occurs, it's very hard to fix the problem or modify the defined gesture. Another approach is declaration-based authoring. The gesture is defined by high-level language, and a gesture can easily read and modify the gesture definition. But users are required to learn the gesture language and need to some effort to create a gesture. Several systems combine the advantages of demonstration-based and declarative approach. For example, Gesture Studio allowed users to demonstrate touch strokes while their sequences are defined in a declarative manner. But because each method defines separate features, the limitations of each approach still remain within individual features. This work is also inspired by visual gesture definition systems such as Event Hurdle. Event Hurdle allows graphical gesture authoring based on hurdle scheme. But the interface of Event Hurdle was too complex to be used on mobile devices, and its recognition was inaccurate compared to programming by demonstration. M.Gesture system is based on the lessons from literature review and a formative study. The goal of our research is to let users to understand the behavior and constraints of accelerometers. It should be easy to learn and use, and the definition is to be intuitively modifiable. Our formative study informed that our participants preferred the simple and subtle gesture motions. Most of their gestures were linear or a 2-dimensional. Participants also preferred the single device gestures much more than multi-device gestures. And when they defined two device gestures, about 90% of their motions were synchronized. Please read our paper for more detailed information about the formative study. We present M.Gesture, a gesture authoring application using the accelerometer values of diverse combinations of mobile devices. The accelerometer values are visualized with the physical metaphor of mass spring. A gesture is defined by demonstration and declaration. The sensor value trajectory is visualized in 3D space. Then the user declares the gesture trajectory using a graphical gesture ordering scheme. M.Gesture visualizes sensor value using a metaphor of mass spring. The system shows a virtual ball on top of a spring that is attached to mobile device. If the oscillation can be ignored, the mass is affected by inertial force and gravity, which means the position of the ball is solely determined by the accelerometer values. The mass spring metaphor allows users to understand the behavior of accelerometers, and they can predict how the sensor values will be changed when the user enters a gesture motion. An intuitive representation could be the gesture's direct path, but we did not use it because of its inaccuracy of the sensor. Another direct representation could be the acceleration value itself or a damped mass metaphor. But the early users who experienced our system without the metaphor thought its behavior was unpredictable. We then came up with the mass spring metaphor. It was the result of design decision to make accelerometer-based gesture in a way that human can understand while technically feasible. A gesture is defined by demonstration and declaration. In terms of demonstration, a user can quickly and easily define a gesture with a single demonstration. It calculates the distances from input trajectory and defined trajectory by dynamic time warping algorithm. Dynamic time warping is one of the most common algorithms for comparing two trajectories. A hurdle-based gesture scheme allows users to graphically specify the range of trajectory paths. A hurdle is a plane that detects intersection of input trajectory. The sequence of hurdle intersection can be defined by user, and it is represented as a series of arrows. A hurdle plane defines the range of allowing trajectory. A short hurdle defines narrow and accurate gesture trajectories, whereas the wide hurdle defines brief and diverse trajectories. Our interface allows the users to easily create, modify, or remove hurdles with a single stroke touch input. Because a user can visually detect the intersection of input trajectory with the hurdle, she can intuitively determine where the hurdles should be located. To sum up, our hybrid gesture authoring allows users to easily create the first gesture and then visually change the definition as they want. We conducted 2 studies in order to answer 3 questions. Is it easy to understand the concept of mass spring? Do users easily learn and use M.Gesture? Is it precise and fast compared to conventional algorithms? We conducted a lab-based task completion study with a post-survey. We asked 20 participants to compose and correctly perform 3 gestures as illustrated in the slide. We designed the 3 task gestures subtle and simple as we found in the formative study. The later tasks are designed to include more complex operations from demonstration, hurdle declaration, and handling multi-devices. We gave the overall instruction about our system to participants, and before each task, we explained the necessary functions, and they had enough time to practice those functions. The whole study took about 25 minutes per one participant. Every participant completed all tasks except one failure in task 3. The average time to compose and test a gesture was less than 100 seconds. The biggest portion of the task completion time was hurdle authoring and modification. 90% of gesture authoring took less than 2.5 minutes, and it can be improved considering all participants were the beginners. In the post-survey, participants answered the easiness of our system in 5-point Likert scale. 100% answered the concept was easy or very easy to understand. The overall easiness was evaluated easy or very easy by 85%. Participants were positive about M.Gesture's interface and function in general. One participant said it was good to visualize the noise of the accelerometer, which is an important constraint of the sensor. Another participant said participant liked the hurdle scheme for allowing him to control the range of trajectory. However, some usability issues were also raised. For example, it was hard to see the interface screen when a user performs a gesture with rotational motions. To evaluate the precision and processing time of M.Gesture, we compared it with its original algorithm, dynamic time warping. We defined 12 gestures from a reference and recruited 20 participants to perform all gestures. In the graph, the top is dynamic time warping and the bottom is M.Gesture. As you can see, M.Gesture was 4 percentage point more accurate, more precise, and 26% faster than the original dynamic time warping algorithm. The conventional dynamic time warping calculates all distances from the input trajectory and defined trajectories, which needs intense processing resource. But M.Gesture system performs the hurdle test first, then prunes unnecessary candidate gestures before calculation. The hurdle test saves the processing resource and is an important aspect in mobile computing. There are some discussion points of our hybrid definition. As mentioned earlier, it made the recognition much faster than its original algorithm. Second, a user can flexibly define a gesture between programming by demonstration and declaration. She can quickly define a gesture with minimal number of hurdles. Otherwise, she can spend some time in elaborating the gesture definition using many number of hurdles. And lastly, our hurdle scheme was simplified by the supplementary information from demonstration. If a gesture must be defined only with declaration, then the gesture expression must be very complex in order to specify various gesture features. We also found some limitations and features of M.Gesture system. Because people constantly make movements in everyday life, a guidance system is required to make gesture designs more robust to passive noisy motions. There might be some undiscovered problems since we did not conduct a long-term field study. Our system may support advanced users in the future, such as interaction designers, programmers, or SIGCHI researchers who want to easily create and modify gesture interactions. We propose M.Gesture system that allows the accelerometer-based gesture customization using physical metaphor of mass spring with a hybrid approach. M.Gesture was evaluated to be easy to understand, learn, and use. The performance of a hybrid authoring was slightly more precise and much faster than the original algorithm dynamic time warping. Thank you for your attention, and it's time for Q&A.
Hi, Gregory Abel, Georgia Tech. Did you get a chance to try seeing how creative people could be with this tool? In the study you reported here, you gave them gestures to do. Did you give them a chance to try to explore gestures that they would come up with on their own?
Actually not. They were given only designated 3 tasks. But yeah, myself, I sometimes play with this system and try to compose as many gestures as possible, but it's kind of similar to what I found in the formative study. People don't want to use some very complex gestures like in a 3-dimensional space. It's completely unusable.
I was just wondering also, you give only one example. So how do you know whether that gesture would be recognized in the future if you have only one kind of training example for it?
You mean the accuracy-wise?
Yeah.
In this study, I measured the precision of our system, and we collected 1,000 gesture motions and compared it with 12 gesture sets, and its overall precision was 88%. Thank you.
One question. You showed that it is a 3D space that they're performing the gesture in, and then most of your hurdles are in like 2D.
Yes.
Right? Have you seen anything with people working with this and trying to do more in the 3D space and any challenges they're having there?
That's a very important question. There can be, because the gesture is defined in demonstration and declaration. In terms of demonstration, it's full 3D. There's no difficulties in distinguish between gestures. But in declarative manner, as you said, it's designed in 2D space, and some academic people ask me if they can compose in 3-dimensional spaces. But yes, actually, it's the constraint of our system. But as I said, most of users generally define a gesture like linear motions or 2-dimensional motions. So we thought 2D space is enough for defining a usable gestures.